Alright, welcome everyone to another live stream. Um, Today is gonna hopefully be a bit longer than yesterday. We only did an hour yesterday. Well, let's take a look where we left off last time. If it even runs, because I'm not even sure we ran anything. Yeah, we're still running. So we implemented very basic Beer's law. We added a little slider for changing the refraction index of the water. And we made the triangles move up and down a bit. I'm still not 100% sure whether this refraction is actually correct or not, but we're just gonna use this, and once we have a model, we can test it a bit better. We also made a start with building a bounding volume hierarchy. So what we've done so far is created a construction node. This node is only used for construction, which is it's very inefficient memory-wise, but it will do. We'll just make things easier for now, and then later we can optimize it. And we built the root node for our BVH. Oops, and we set up a stack with grid spelling the word hierarchy. Hierarchy, like that. Let's check that. Yeah, hierarchy. Cool. So let's take a look at the plan for today. So first of all, we'll build the BVH using those construction nodes. We'll optimize the BVH construction nodes into GPU-friendly formats, which is that other structure that I just showed. Then we'll upload it to the GPU. We'll make the vertex buffer of our model readable in the pixel shader. We'll implement ray X-line bounding box intersection. We'll then implement stack-based BVH traversal using that AABB intersection. Then I might want to do some visualization to see if our BVH is any good. And we'll add some performance counters and perhaps even a heat map mode so we can sort of see what's going on with how efficient our BVH is, since I want to try a bunch of different types of BVH. So let's get started with building the BVH. So we need to calculate the optimal split plane. Well, optimal is a big word. We're just going to look for a good enough one. We went over this in our last image. Like, if you split them sort of uniformly, you get a pretty good BVH. But if you, for example, split like this, where you have like one big box and one really small one, that's not a very good BVH. So I'm thinking we should first just try to do a median split. And with a median split, we always cut in half. Yeah, let's try that. So we'll figure out the longest axis first. Oh, hold on, I need to set up the current element, otherwise this won't work. Is the root node. I also want to keep track of depth for this, because at some point we need to stop building the BVH. If we're gonna have an ABB around every single triangle, it's not going to be efficient. We want to have like groups of 8 or something like that. Depth is going to be 0. So let's find the length of all the axes. Axis lengths, which is going to be just subtracting the max from the min. Then we figure out the smallest index, so we'll assume it's smaller. Shortest axis is 0. We'll assume it's the first one, and we'll just check. Right, so if axis length 1, or the y, is shorter than our current shortest axis length, we'll make the shortest axis length equal axis length 1, and we'll put the shortest axis equal to 1, and we do the exact same thing for number 2. And then after this, shortest axis will hold the index of our shortest axis. Oh, I'm doing this the wrong way around. This should be longest. Longest. When I cut along the longest axis, not the shortest. Oops. Oh, everyone makes mistakes, right? Cool. So right here we test if other axes are longer. Cool. Let me do something real quick on my other monitor. Cool. Awesome. Yeah, so we got the longest axis. Then what we shall do is determine the split plane. Like where on that axis we're going to split. And that's simply going to be the middle. So we'll say we'll take the min and then the longest axis plus the current element max and the longest axis, and we'll take the average of those, and that will give us the center between them, the halfway point. And I'll write it like this, so it's a bit more readable on a couple more lines. Cool. We can't really check if we need to split or not. So we'll actually move this check up here. Like we don't have any heuristic that we can follow for that. We'll just say if stack dot current element dot depth. Oh yeah, hold on. Current element dot depth is greater than, let's say, 12. I don't know. We'll just skip this. We'll just not cut. Hold on, we need to pop something up the stack. So stop if the stack is empty. Pop an item of the stack. And then continue. So here we sort of have a maximum traversal depth. What we also might want to add is a maximum, like a minimum number of children it needs to have to split. So we can also do that. Or like a maximum minimum of triangle count. So if it's less than 8 triangles, Uh, if there's an 8 triangles, we also won't split. No reason to. Awesome. If we not need to split, keep this, skip this node. Alright, so we do this count size based on heuristic yet. Alright, then we need to split the nodes. So first we allocate 2 nodes. Let's make these a bit more visible as like the steps that we go through. Cool. Allocate nodes. Is it node count? Yeah. So we allocate them based on the node count. So we're doing a linear allocation. And node right. So that allocates the nodes. That makes me think at the end we'll want to make sure that our node count didn't exceed our maximum expected node count that we allocated. Right here. So we'll calculate this as the maximum node count. This should be less than or equal. Did I have my own macro for this? I do. Yeah, let's do that. Use that then. It's always good to place assertions in your code so you can sort of verify that things work. Sort of like a simpler version of a unit test. Next up, we want to split these. So what I'm thinking is either we can allocate just too much and then fill the arrays, or we can do a run where we like keep track of a capacity and a size, and as we go past the capacity, we double the capacity, which would also allocate too much and be a lot of memory allocations. Or we could do dry run, where we first calculate the number of triangles in the left node, number of triangles in the right node, and then allocate once, then fill them. Let's think. I think option 3 is best because we can also do the dry run when we implement the surface area heuristic. We have to go over the triangles then anyway. So yeah, let's do that then. So we dry run to calculate try count left and try count right. Let's see. So we'll load the triangle indices. And again, we're not making it very efficient, like having these multiplies in here. No reason to have them here, but let's just try to get something running and then we'll make it efficient. So we load the vertices. And then we need to decide the side on which side of the split plane we'll put it. And there are a couple of ways to do this. One is to just use one of the vertices to decide where to put them. The other is to use the center, based on the center, decide where to put them. Trying to think of what would be best. Let's just do the center. I think center is fine. So we only need to take our split axis into account. And then we'll just do this. Cool, then we have the center. Then we can decide whether to put left or right. So put left equals center is less than the split position. Or we can just stick this in the statement. So let's have a count left and a count right. And let's initialize those to 0. I don't like these braces here. I don't know why. Yeah, like that. Perfect. Yeah, so I either put them left or right. That's it. That's our dry run. Then we can allocate. And one thing we can assert right here is that our try count left equals our try count right. No, our try count left plus try count right equals our current node try count. Make sure we did not lose track of any triangles. Because if the left count and the right count of the children won't match, then, well, if they don't equal the number of triangles in the parent, that either means we somehow got an extra triangle or we lost a triangle. Both cases are bad. Should never happen. So we'll just copy paste this code. No, let's do allocations first. So we allocate triangle buffers for children. And we can assign the try count in here. indices malloc is 3 times try count left. Types. I'll do the same with the triangle count right. Cool, so we allocated those. Now we can do our real run. And what I'll do is set try count left back to 0 and try count right back to 0. We can use these as our indices in the arrays. So now we actually sort triangles between children. So basically the first part of that loop is going to stay the same. This is just going to be a bit longer. I will just put the indices in there and then increment the number of triangles. And we do the same for the right side. Oh, accidentally duplicated. What is Oh, Control D is duplicate. That's useful to know. Awesome. So store triangle in left child. Store triangle right child. And here we'll assert left count is the same. Assert right count is the same. They should be the same as on our dry run. If they don't match, something went wrong and we have a bug. Perfect. I will also assert again that we did not lose track of any triangles. Well, this can never trigger, because if these are the same, it means that we went past this. Well, for us to even check this, we need to have went past this, and if these values match, it matches this. But just in case we go out of bounds somewhere, this sort of stuff might catch it. Yeah, that's the triangle splitting. Let's look at the rest of the data. So node left, children should both be 0. Let's do this at the top of this when we first allocate them. So we'll do some set some basic data, or just initialize the nodes, the child nodes. Is there anything else we want to set right away? We're going to overwrite this, we're going to overwrite that, and we're going to overwrite that. Alright, all is good. All is well. Clean the list of triangles on this node. Yes, we can do that now. So we can set our children to node left and node right. and we can do, we can free this pointer, no longer need it, and we can say, whoa, I don't know what that is. Try count, oh, try count 0. I'll just call this convert current leaf node into an inner node. And lastly, we'll generate bounding boxes for the child nodes. Or yeah, we can do this. Let's see if we can just copy paste this for a bit. Copy pasting things makes it easy. And let's call this C for child. And this should be, we'll just call this node. So instead of root nodes, it will just be nodes. And I think we can even drop this in a function later on, since this is practically the same as the other code. And here we'll copy the ABBs in our left and right nodes. Then we are done with our current nodes. And we will push the second node into the stack. Node to be put on stack. And let's actually slice it like this. Dot node equals node right. And depth is going to be the current element of depth plus 1, since we're 1 deeper. And then to put it on the stack, we just do this. And then we shall make our current element, the depth, we'll just increment it by 1. I'll make our current node left. I will continue looping. And we got our exit condition right here, as soon as we pop things up the stack. This should actually check greater or equal if you want it to be depth of 12. And we'll just have to assume this is large enough. So what I'll actually do is just say assert that our stack index is less than or equal than stack size. I'll make this a macro, or just a constant. Once we actually start traversing the stack, traversing the BVH, we don't need nearly that size of a stack, but for now, let's make it big enough. Cool. Let's see if we can run through this code without crashing. And we can do some we can actually do some checking on the data to see if we got anything that looks even remotely right. So in our game code, let's call test build BVH. We don't even output a BVH yet, that's fine. Just want to test building it, and we'll do that right after we load our model. So let's run, see what happens. Everything seems fine. Let's check our node count, 25. With a maximum node count of like 288,000. So that might actually not be right. That seems like very little nodes, very few nodes. So we had a maximum depth of, let's see, 12. So let's think about that number. How many nodes could we get if we were to split every time until depth of 12? Assuming we always had enough triangles in the nodes. Let's get out Notepad. So let's just write down some numbers and see what ends up happening. Perhaps we can figure out a little formula that we can use. So depth 1 is 1 node, depth 2 is 3 nodes. Then if we split those again, we get 7. If we split those again, let's see. So if the 7, and then we have, well, this is 1 plus 2. It's 1 plus 2 plus 4, and this is 1 plus 2 plus 4 plus 8. So this is always equal to, this will equal 8 times 2 minus 1. And this is step 0, 1, 2, 3. So it seems to be 2 to the power of step, or depth, times 2 minus 1. So now we just fill in the depth of 11 is the highest depth index we'll get. So this would equal, let's open console count, to the power 11 times 2 minus 1. That's a lot more nodes. Let's actually add some braces to make sure this is right. Yeah, that's a lot. That's more number than I was expecting. So we would expect somewhere up to 4,000 nodes. Somewhere in that range, maximum. So it's definitely this condition that is causing us to have way fewer nodes. What we also don't check, that I want to assert, is what happens if we have 0 triangles on one side. So we don't handle that case right now. We could be, oh, I hate this. I hate the, yeah, I hate the edit and continue. Never works properly. Yeah, so we never have the case where we have 0 nodes. What happens if we remove this case? Still 25. So something is going wrong. So then it is the first case that is messing it up. If our depth is greater than 12, then we'll continue. Well, we stopped reversing. That is not the number I was expecting. Do we allocate correctly? Does our node count even... Is it even correct? Yeah, we incremented twice. Hmm. Something is going wrong. But what is going wrong? Let's test a bunch of different maximum depths. See what happens. So let's say 1. So this, well, 0 will create, we'll just have just the root nodes. With this, we'll have 1 split. So we expect 3 nodes. Three nodes, all right, that's correct. Let's have maximum depth of 2. 5 nodes. Does that match? We would expect 7. But we get 5. Oh, this is the problem. Instead of checking if there is anything on the stack, we'll pop something on the stack. Right here we check if something is on the stack, we'll stop. So right here we need to test if the stack is empty. So if we run again, I would expect to get 7 now. Seven, yes. So what happens if we go back to 12? And we fill, but do we fill in a place where I would expect to fill? Yes. In this case, we have one triangle, we try to split it. So we'll add the test back to see if we even have like a significant number of triangles to split. Perfect, around 8,000 nodes. That's actually pretty reasonable to get for maximum depth of 12. So no, wait, that's actually not reasonable. That's double what we expected. Let's see, if it's 0, we expect 1. Or oh, I should insert 12 here. Yeah, 8,191. Yeah, it's a little bit less than that. So that seems fine. So let's output some debugging data that we can use to sort of analyze what our BVH looks like. So what I want to do is just go through all the nodes, and because all our nodes in a linear array, it makes this super easy. Nodes I. What I want to do is first count the number of leaf nodes and the number of inner nodes. So if a try count is greater than 0, we'll increase the leaf node count, and else we'll increase the inner node count. And we can print those values. Let's add 2 new lines here. And the other thing I want to do is I want to print all the triangle counts of all the leaf nodes. I'll just print out the numbers so we can stick it in Excel. Yeah, let's run this. Add a new line here. Couple of new lines, and then add it like that. Done building. Or done outputting data, doesn't really matter. Cool, so our console should be full of juicy data. So somewhere at the top, right, we got 4,000 leaf nodes with 0 inner nodes. Ah, we didn't increment. That's obviously not going to work. If we don't increment the variable, then nothing happens. Right. Let's see. So we got about the same number of inner nodes as leaf nodes. That makes sense, because we always split in 2. Yeah, this actually matches like our total node count is double the leaf count minus 1. Cool. And then we got all this juicy data. Well, copy over. We might actually get away with a bit higher maximum depth for a better BVH. Let's open LibreOffice Calc. Drop the data in there, yes. We'll say the average of this. We'll say minimum is min. Something fell over here. Sorry about that. I don't know how loud that was in stream. Right, should stay there now. And let's also do maximum. Oh. Let's also do a median. Right. So our minimum number of triangles is 2. Our maximum is 277, which is actually pretty high. Our median is around 26, which I also think is still pretty high, and average 35. So let's increase our maximum depth a bit and see what that does to our BVH. Perhaps we get a bit better numbers if we do that. So let's make the maximum depth 16. According to C, we get a lot more smaller numbers. So we also get way more nodes, which is fine. This is a lot of data to copy. Pretty annoying that I have to scroll through this. I wish there was a bit more efficient way to do this. Can I just, what if I just do Command A and copy it in here? Yeah, and then just get rid of the data that I don't need, since that's way less. Oh, there's some data left here. Cool, and then we can grab this, scroll all the way down, cut, put it in there. Oh, more random stuff that we don't need. Cool, and then we can copy this here. Oh, that's way better. So we now have around 5 triangles per node. The smallest number of triangles is 1, which is not that great, but it will do. Let's actually find that one. How many ones do we have? Oh, of course. Can I just say match? Oh, I just want... Like doing this manually is going to be a pain. So what I'm wondering is, if we have the 1, how many triangles are next to that node? Yeah, I'm not gonna find that. Let's count if keep a sign count if. It will give the range, and where did, oh, I got teleported to the bottom. And the criteria is if it's 1. Does that work? Let's put this in quotes. Did I mess up the range? Yeah, so we got 24 cases where there's 1 triangle in a node. That's not great. But it's good enough for a BVH that doesn't use a surface area heuristic, I think. So we'll go with that. Good enough. So now we have this whole BVH using the construction nodes, which aren't very efficient. And we want to smash this down to this more efficient format. And the first thing I'm thinking of is these 2 children pointers. These are really annoying to deal with for smashing it down. Because what I'm thinking of is taking advantage of the way we allocate things. When we allocate these indices, we always allocate them next to each other. So we can just store one of these pointers and now calculate the other pointer by just incrementing 1. Because they're next to each other in memory. And instead of storing these pointers, I want to store the index. So we'll do left child index. And that will hold the indices for both the children. Now there's now one special case that we need to think about. Instead of using null for having no children, for not having a child index, we should use the inverse bits. So the highest possible value. So we'll just initialize that here. And initialize that here. And if we accidentally use this index, everything will break, which is great, because we should never use that index. So right here, I'll just say, well, yeah, we can use node index left, which is node count. And this will be node count plus 1, and then we can just say node count plus equals 2. And we just have to store the left index. And if we actually want to use the children, we can just say nodes plus child index. Cool. And that should give us the same result. So let's see if that works. That doesn't work. We broke it. Let's see where it crashes. So somehow it crashes here, which I was not expecting. Right. We don't use the index here, so we didn't calculate the BVH, the access line bounding box around it, which caused it to do a split with bogus values, which caused it to put everything on one side. Yeah, now we get the same data. Yeah, that looks about the same. Cool. So the next step in optimizing this is we want to get rid of this array because this pointer is large. Let's also recalculate the number of bytes that we have. So this is 24 plus 4 is 28 plus 4 is 32 plus 8 is 40 bytes. So we save 12 bytes by just doing this little trick. Now I want to get rid of this pointer and make this an index in an array. And this is actually more efficiently to do this when we optimize the structure into a more memory efficient model. So let's actually do the optimization step. And what we'll also do in this optimization step is that we have this child left index, I'll just call child index here, and we have a triangle index. And we only need either of these two values at a time. We never need both of them at a time. Because we either are an inner node and we need to represent the children, or we are a leaf node and we need to represent an index into triangles. And we determine that based on the triangle count. So we will just check if the triangle count equals 0, then this is a child index. And if the triangle count is greater than 0, then this is a triangle index. Yeah, so let's go build that. And that will bring our BVH node down to 32 bytes, which is really nice because 2 BVH nodes will then fit in a cache line. And more will fit on a cache line on the GPU, I believe, but I'm not sure about the number. I can look that up real quick. If they even make that public information. They might not do that, or they might have like different sized cache lines for different types of caches. Yeah, I'm not sure about it. But it's probably power of 2, and powers of 2 always fit in powers of 2. So having this size of power of 2 will make it nicely cache aligned. Alright, let's go build that. So what we can do now is, for our new nodes, what should I call these? Because I already have nodes. Let's actually rename nodes to C nodes for construction nodes. Let's see where it also would break. Right there, right there. Alright, that should be fine. See if it still runs. It's taking a long time to do this now, the building. As you can see the load time. Yeah, we'll create BVH nodes. So BVH nodes equals and we can just reuse the node counts. And then what we need to do is allocate an array in which we can store all the triangle indices in a way that they are packed together based on where the nodes are. So we cannot reuse our index buffer because the triangles are not packed together based on in which nodes they belong. But what we do know is that this triangle index buffer is going to be the same size as the index buffer we already have. Made a typo there. That fixes that. Cool. So now we can just simply go through all the nodes. And we can load the C nodes. And we'll have two cases. Either it's an inner node or not. So we'll do check if it's greater than 0, it's a leaf. Otherwise, handle inner node case. In this case, we'll just say nodes I dot min is the same for the max. We'll copy that. That part is actually the same whether it's a leaf or not, so we can just put it there so we don't repeat ourselves. Try count is 0. We can actually just copy the try count. Just store the child index. And what we do now is we need to keep track of a location here. So the index in our index buffer, just to not be confusing at all. This is going to be that index. And then we can increment that index by the triangle count times 3. So the index will be based on The index will be in indices, not in triangles. Or should we do that? Not do that. Let me think when we're trying to read it. We'll be looping through triangles. Yeah, because otherwise we need to do an extra multiplication at runtime. So increment. Let's call this offset instead of index. Yeah, this is actually just a triangle buffer. It's not really a triangle index buffer. It's not indices to triangles. But this is the index in our triangle buffer. So now we need to copy the indices over. So our destination pointer is going to be the triangle buffer plus the tri-buffer offset. Our source pointer is going to be C node triangle indices, and the count is going to be the C node triangle count times 3 times the size of our index. And then we can also free the old pointer that we no longer need. Cool, and that will convert our inefficient nodes into efficient nodes, and then we can also now just get rid of the old inefficient nodes. Don't need them anymore. Cool. So let's see if all that works. We did crash, so I'm just going to assume that it works. We haven't tested it, but we'll do that in the next step. So we built the BVH with construction nodes, we optimized it. Next step will be to upload this BVH to the GPU, and then we can actually start using it. Before we do that, I'm going to take a short break, because I need to go to the bathroom and refill my water, get some more tea. So yeah, I'll be back in a couple of minutes. All right, let's get going again. Um, let's see how we're gonna upload this BVH to the GPU. So let's look at the data that we have right now. We have this array of nodes, and we have this big triangle buffer, and then we have some counts to keep track of stuff. So basically, just a node count. Let's put that in a structure. We'll call that the BVH. Oh, I also put the braces wrong on these. I prefer them like that. Perfect. And we'll simply just have an array of nodes. We'll have an array of goes to the try buffer, and we'll have a node count. And that's it. That's our BVH. Then our test function is simply gonna output a BVH. It's not 0, it's the node count. Awesome. Cool. Let's also get rid of all this, well, let's just comment out this this printing stuff. So this is like the most basic, simple BVH that we can really build. But this will already immensely improve the performance of ray tracing any 3D mesh. Delicious tea. So let's also just stick the BVH in our game memory. Cool. Then when we upload our test model, we'll also upload the BVH. Let's find our graphics interface. Upload test model, BVH, BVH. Cool. Now we can create some more buffers for our test model. Test BVH nodes, node buffer, BVH try buffer. So we have two more buffers that we can fill up. Create BVH node buffer. Well, I'm just copy pasting the code without thinking about it. This should be node count times the size of BVH node. Bind flags. We're just gonna bind this as a shader resource. CPU X flag 0, that's gonna exit from the CPU once we've uploaded it. Structure byte size is the size of a BVH node. The slice pitch is going to be the same. It's a 1D buffer. We don't need any pitches or slice pitches, but we'll just put them in there just in case. The node buffer. Cool. And if we fail, well, crash. The best type of error handling. Failing is crashing. We should just never fail. Again, just mindlessly typing. This should actually be the index count times the size of EM32. This is going to be the same size as our index buffer, but it's going to have different data than the index buffer. And this is going to have different usage. Well, same usage, but different binding. Cool. Yeah, let's actually create that buffer. So we've created the buffers. This will upload the data. Let's test if that works. Cool, didn't crash, so the data's there. Now we need shader resource views to actually access that data from our shaders. So we'll just add these here. And we'll need one more shader resource view. For the vertex buffer, since we need to access the triangle vertices. It's going to take the resource, then it will take an SRV description, and then it's going to output the SRV. So let's create the description. And then we have a lot of data to fill. Let's see, formats. I think we put this at unknown, since our buffer is a custom size. View dimension is definitely going to be a buffer, although we might need buffer extended. Let's check buffer extended. So it wants to know different things based on different let's look at the documentation on MSDN. So, alright, the buffer SRV as a raw buffer using information from shader resource view. Raw views of buffers. You can create resources that are strongly typed or typeless. You can control whether resources have both read and write access. You can make resources accessible to only CPU, GPU, or both. Up to 128 resources can be active for each pipeline stage. I've never gotten close to that number. Direct3D guarantees to return 0 for any resource that is accessed out of bounds. The life cycle of the Direct3D resources. Create a resource using one of the create methods. Bind a resource to the pipeline using the context, and then deallocate using release. This enables runtime to optimize access, especially if the resource created with a flags indicating that it cannot be mapped by the application. Resources created with a specific type cannot be reinterpreted using the view mechanism unless the resource is created with the DDI bind present flag. D3D10. This is D3D11. If set render target or shader resource views can be created on these resources using any of the fully typed members of the appropriate family, even if the original resources is created as fully typed. HF formats. You specify the size of the memory, allocate by the runtime, and generate the subject textures on bitmaps. We don't care about those. You can think of a raw buffer, which can also be called a byte address buffer, as a bag of bits to which you want raw access. That is a buffer that can conveniently access through chunks of 1 to 4 32-bit typeless address values. You indicate that you want raw access to a buffer or a raw view of a buffer when you call one of the methods. Well, I know I want a structured buffer in this shader, so let's look up how to do that. Right. Yeah, and then we can do read-write buffers and textures. The structured buffer. It's a buffer that contains elements of equal sizes. Use a structure, yeah. A single member like this. So I think we can just use buffer and not need the extended thing. Buffer. And then we'll say buffer. We care about either first element or element offset. How do I know which one of these I need to fill in? Oh, a bit of stretching. So we have like this, and this shares memory. So we can only set either of these two. And we'll read it based on the context. Number of bytes between the beginning of the buffer and the first element to access. The offset of the first element in the view to access relative to element 0. So I think in this case it's element offset, because we defined the size of our element. And it's also probably num elements that we care about, not element width. This can be determined from the format stored in the shader resource view. Or it's the other way around, because we use the unknown format, because it's a custom data type. So it would be element offset in bytes, or first element. And then it's the element width. It actually doesn't matter which of these you fill, since they they share the same pieces of memory. But the value that you put in them depends on our context. Number of bytes between the beginning of the buffer and the first element to access. Yeah, so whether it's num elements or element offset, it's going to be 0. So we don't really, well, whether it's going to be first element or element offset, it's going to be 0. So we don't really care about that. I do care about this. Which one of these does it want? Let's just try one of them and see if it breaks. If it breaks, we'll know we need the other one. Alright. Now let's do the other shared resource view. I'll just copy this. So format is R32uint. And then in this case, it's not going to be element width, but it's going to be the num elements, which is going to be index count. I find this structure to be really strange. The documentation is not very good on it, I think. The width of each element in bytes. This can be determined from the format stored in the shader resource view description. Yeah, but we cannot determine this in our case, so we need to give it the width. But in this case, it can determine, so we give it the number of elements. I think. Alright, let's then create a shader resource view for our vertex buffer. Now there is something to consider here. We can either just add the bind flag here to also bind it as a shader resource view, or we can create a second buffer that holds the same data that just has the other flag. And it might be that the second case could be a little bit more efficient, but I think we should look into that when this might actually become a problem. So in this case, again, we we're not using a default format, so it's none of these. So format unknown, and here we give the element width. Element width. There we go. What do we call that variable again? SVB SRE. Cool. Let's see if any of this crashes. It crashes. Let's see where. Line 1432. 1432. We crashed here. Invalid arguments. Let's see what's up. The format unknown cannot be used when creating a view of a buffer. So it's obvious we're doing something wrong. It says this is not allowed when we're doing a buffer. Should we do a buffer extended? What is this even for? It's not a raw buffer, it's a structured buffer. The resource is a buffer. And if we look at all the DXGI formats, yeah, like these are all, none of them is like custom format, user defined format. Perhaps we can find something about using a structured buffer online. See if we can find an example. Create structured buffer. So here I just, oh, we need a miscellaneous flag for structured buffer. Let's see. Let's add that. Yeah, this one is not a structured buffer. That's just a regular buffer. A buffer, 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 buffer. Still fails. Cannot specify any of the following listed bind flags. So we're not allowed to bind it as a vertex buffer if it's also structured buffer. Okay. So I think we have to re-upload it then. Let's just get rid of this for now. See if we can even create the BVH nodes. Now it seems to be working fine. Yeah. It's just missing that miscellaneous flag for structured buffer. Cool. Then we need to create a BVH vertex buffer that we can use on the GPU. D3D11 buffer misc. What was it called again? Oh, resource misc. I actually want to look up a bit more about this flag. Perhaps there's some other constraints that we need to think about. Yeah, I think we already found this article. Yeah. Okay. If there are any other constraints, we'll just find them as we go along. Buffer. So what I was saying about having to create another vertex buffer, being more efficient, actually turns out to probably be true. Because we cannot even bind it as a vertex buffer if it's a structured buffer. System memory page is going to be the size of vertex times the vertex count. Test BVH vertex buffer. Perfect. And if it fails, will crash. And then we need to create that shader resource view for it. Let's do that based on the shader resource view. So actually you have to re-upload all the model data just for the ray tracing. I was hoping we could share the vertex buffer, but that's not the case. It's probably only a couple of megabytes though. It should not be too bad. Yeah, this should be all. Cool, let's see if that runs. Cool, everything seems to work. Now we can do some more shader programming. Actually, I also want to change the watercolor a bit because I made it really blue, even though I was going for like a slight blue. So let's make it slightly blue. Yeah, here, Beer's Law. So it's actually meaning to do something like this. So we can actually pick a color in paint.net in the color picker. So yeah, like a slight blue is still a lot of red and green. And lots of blue. That's still really ugly, but it's better. Let's make it a bit more blue. I don't know. It's now a slight color change. Perhaps someone has measured this constant for water. Yeah, so we should be able to bind these. This is going to use a texture register. pH nodes. And we can just copy what's in our structure on the CPU in there. Like that. And actually maybe better to fill this data like this. So this float 3 is on a 16-byte boundary. Not sure if that matters, but let's do it just in case. Yeah, BVH nodes, and then we can also do vertex. Which is position, normal, text chord, tangent. Well, I need to add semicolons. Instead of a structured buffer, this is just going to be a buffer of uints with the indices. So perhaps we can do like slightly faster loading or something with that. I'm not trying to optimize too much, but it's always good to do things that are generally more performant, so you don't lose, so you're not like suffering a death from 1,000 little cuts. Yeah, so we have our triangle intersection. Now we need to bind these buffers. In our rendering code. See, this is height map generation rendering. Perfect. So now, let's see. Draw plane, water plane. Why do we even bind the sampler? Oh, we bind the sampler for the skybox. That's right. So here, bind the shader resource views. Comment is wrong. So what I want to do is write it like this. That is not. Oh, is it try it? Oh, it's just this. Cool. Keep forgetting what I name things. So now we only, like, if you do it this way, you only have to do one API call. One API call to set all these shader resource views. And these match like 0, 1, 2, 3. And sent integer. Yeah, that seems fine. Do I need to upload the node count? I don't think I need to, since we're just traversing. So as a test, well, don't really need a test. Let's look at our goals. So we made this. We uploaded the BVH to the GPU. This one we didn't do. We created another copy of the vertex buffer for the BVH. So next up is Ray axis line bounding box intersection, and then we want to do the BVH traversal. Yeah, let's just look up a simple intersection. Is this what we want? Sort of like this. This does do the optimization where you get rid of the divides and replace them with multiplications. Yeah, no, you want to replace this with min and max functions. Early exit. Let's actually look up ray ABB intersection in HLSL. That's not how you want to do that. You don't want to have a loop in there. Oh, that's better. Don't want to do that in the intersection though. An efficient slab test. They add to their knowledge this important efficient slabs method used by industry ray tracers is not widely known. It feels like they're missing a check. But this does look awesome. Let's do this. Does this always work, or is this like a... Let's look a little bit further than this. Let's keep this in mind, because I'm not sure if this is like a full-on correct test. And also this doesn't add the depth. Because if you use the... you can sort based on depth and then figure out huh. I'm generally confused by this, whether this will work. Because it looks close to something that that I think I've used before. Sample code. 44 megabytes. Oh, they have like a bunch of files. Can I just open this with VS Code? Yeah, that's fine. Just determines whether the ray hits the X-line bounding box. Box center, box radius. Define test UVW. Let's look at that other file. Oh, it doesn't like that. Or double click. Yeah, this also seems really strange to me. Huh. I mean, if this works, that is awesome, but it's weird that it doesn't calculate the depth of where it hit. Perhaps it's just... Let's look for some more efficient Ray ABB algorithms. Yeah, this looks a little bit like what I'm used to. Yeah. Now let's compare these two. So these 6 checks that they do here is the same as these 2 lines. Then they take the minimum of T0 and T1. Yeah, which is the same as these 3 min checks and these 3 max checks. Those are those. And then, yeah, they do this max and this min to figure out T min and T max. And if the T min is less than or equal to T max, it hits. But they don't check for T max greater than less than 0. So they don't test to see if the X-line bounding box is behind. But I think this is the way to go. And I think we can do like an out T. And we'd also need to check that T max is greater than 0. So this might not be as efficient, but this might be more correct. Or it handles a few more cases, and we'll just have to benchmark. So we'll do we care about checking if the ray is behind ABB? Another do we care about outputting the distance for the ray ABB traversal? Um, what I'm thinking of now is that um, our model, like the local space or model space vertices, are not at a position that we can see them in the water. So we might not even we won't even see the ABV if you try to traverse it. So we need to transform the ray, but I don't want to get to the retransformation yet. Actually, we can draw the rabbit, the bunny, without any world space changes. Let's see, where do we draw that test model? Yeah, right here. So without the world matrix. So we won't rotate it, translate it, or anything. Unexpected token buffer. Oh, semicolon. Oh, out floats T. Another error. Oh, this should all be float 3. Also not sure about min component, max component in HLSL. Intrinsic functions. Count bits. Is there even an intrinsic for that? Is min component even a function? Yeah, I think we just need to implement that ourselves. That's not a problem. That should solve our case. That section called that X is really confusing. It's called V for vector value. Let's make this naming consistent. Doesn't lock. Oh, yeah. Forgot to rename that. Oh, semicolon. Forgetting all these semicolons because I'm doing so much programming in a language that does not use them. Cool, so stuff still compiles and runs. Let's see where our bunny ends up. Yeah, there's no way we are going to see that. What we can do, instead of ray tracing the refractions, ray trace the reflection. Because we can see that from the water. So we can do some testing before we actually transform rays and move the model the way we want it to. Okay. So let's build a reflection ray. And then for our ray, we also want to generate an inverse of the direction. Or just reciprocal of direction. And what this reciprocal will do is, instead of having to divide by direction, we can multiply by the reciprocal of the direction. It's simply using the rule that x divided by y equals it equals x times 1 over y. And doing multiplication, since doing multiplications is faster than divisions, we just divide once, and then we can reuse that reciprocal for all the ABB tests that we're going to be doing. So I think that was also an intrinsic for the reciprocal. So we might want to use that. Oh, that's an approximate. Should we use that? Oh, it needs Schermo 5. I'm not sure if we're using that. So let's just do the divide. Cool. So let's load our ABB, or just our first node. Node is going to be BVH nodes 0. That's going to be nodes min ABB, max ABB. We're going to output T. Yeah, we'll hit, what's this? So if we hit, let's say if we don't hit, we're just gonna sample the skybox, but if we do hit, we'll set the color to 1, so we get white. Something is wrong about this. Refraction ray, reciprocal direction. Did I make a typo? Oh yeah, it's still called inverse direction. It needs to be reciprocal direction. Error. And the oh, haha. Reflection ray. So we should be seeing a reflect box in here, but we are not. And the box should be right there. I think we should be able to see it from an angle like this. Nothing is showing up. Let's just not sample the skybox at all for debugging, and then let's also get rid of the water. Yeah. So now it just gets dark, and we'll just return the reflection color. Right, but 4. Do we see anything? No. Unfortunately not. Even though I think we should be able to see that. So either we're not getting the data that we expect, or we're not getting the, or ABB intersection is broken, or we just cannot see the model. So let's see if we get any useful data at all. So let's output the maximum color. If it's all going to be 0, that means that we are just reading 0 and not the actual data that we care about. Yeah, that seems to be broken. We're not binding things correctly, I believe. Let's use my favorite tool, RenderDoc, to debug this. Yeah, access, allow it. Cool. So we have 12 to capture frame. We can close the program. I think this is our water part. Mesh viewer. No, that is ImGUI. That seems to be a water. Sea, terrain, water. Cool. Pipeline states, pixel shader. So it does seem to be bound. This is probably the bytes, the number of bytes. Ah, our root node doesn't have an ABB. And for some reason you only have 31 elements. Oh, because we can set the size in here. So our root node is messed up. Let's see if that's also the case in our building thing. That seems really weird to me since we can build the rest of the BVH. So here we grab the first node with a size of 0. So I think it's just doing a split in the middle. Oh, yeah. We never store this. That will solve our problem. Now we get a color for the maximum value of the BVH. Let's do our traversal again. See what happens. Just a reflection. Yeah, there we go. We can see the reflection of the box around the bunny. Cool. Let's add the other stuff back in. Yeah, awesome. Makes it a bit difficult to see with the water effect going on. And as you can see, we're not reflecting the edge of the terrain, so it looks a bit out of place there, but we'll fix that later on. Oh, this is already pretty cool. Yeah, let's just output the reflection color where um, we just draw the little box. Yeah, like that. That is so cool. Now water is just a big mirror. Cool. So we got some useful data. Now what needs to happen is we want to traverse the whole BVH and then intersect with the triangles in the nodes. And then only draw a white pixel if we hit the triangle. Let's look at our goals actually. Let's look at the goals. Yeah, BVH, stack-based BVH traversal. That's the next step. So let's just call it ray BVH intersect. And do we want to, how are we going to pass this BVH? I think we just cannot. So let's instead just pass a ray. And let's output also the distance of where we hit it. Where we hit the triangle. I'll call this out t. Just need to keep track of how far it was that we hit something. Then we need to have some sort of stack. I'll make this like 32 elements. It's already probably too large. And this needs to be uint. I'll have a stack index at 0. Current node index also 0, which is the root node. We'll create an infinite loop. Well, not really infinite, but without a condition in the loop itself right there. So first of all, we need to check, are we in inner nodes? If, let's actually first load the nodes. And here we handle leaf node case. For the leaf node, it's actually fairly simple. We simply do a ray. We will have to loop through the triangles. Yeah, let's create that loop. And then we have to load 3 indices. what did I call the variable now? Child IDX and triangle IDX. So that's going to be the base index into our buffer. Then we can load BVH indices 0 plus 1 plus 2. So here we load triangle indices, and then we will load triangle vertices. What I'm thinking of right now is that we actually have a lot of data that we don't need at this point. So I'm thinking of splitting the position and the attributes of the vertex into two separate buffers. Since we need to have separate buffers anyway, so we might as well. Oh, we made this require the whole array structure. I want to change this, so it just takes origin, ray direction. So if we intersect this triangle, we will test if t is less than our current t, because we only really intersect it if that is the case. I will say t equals t. I will set the hit index, the index in the index buffer which we hit, equal to I index. So that way we know which triangle we hit. And we'll also return the hit index when we finish the function. And we'll initialize this to -1. So in the case we miss, we'll return -1. And if we hit, we'll return the index in that buffer. Awesome. What needs to happen here next is if stack index is 0, so if our stack is empty, we break. Else we say current node index is we'll pop a node of the stack. Alright, if we are an inner node, there's two ways to go about this. One way is just test, did we hit the nodes that we're testing? And then we'd also need to test that for the leaf nodes. Or we can test, did we hit the child nodes? and only put things on the stack and traverse them if we actually hit the child node. So I'll do that. He left. So we'll intersect with those child ABBs. So in the case we hit left and hit right. Want to sort. Else we just hit 1, so if we just hit left, we want to say current node index is node of child IDX and try IDX. Else, it means else if we hit right, the next index will traverse is that plus 1. Else we will pop an item of stack. Because it can happen that we hit the parent ABV but didn't hit any of the child ABVs. And I'll sketch a situation where that can happen in Paint. So let's say we have triangles like this, and we have our parent ABB, and then we have two child ABBs. And imagine if the ray is going like that. Like it's gonna hit this parent ABB, but it's not gonna hit any of the children. In that case, we want to check if the stack index is 0. We break, and else otherwise we'll say current node index is stack. We'll pop an item of the stack. And that should be it. Oh, one more check. We need to test if we hit the root node. Oh, we also need to sort and traverse based on which is first. So if we didn't hit They'll simply return -1. So here we say if t left is less than t right, it means t left is in front. We shall put this in the stack, and we'll make the current node index the left one. And if it's the other way around, we'll put the other one on the stack. We'll put the left one on the stack and reverse the right one first. Because also every time we're going to hit stuff. Oh, that's also another checkup we need to do. Yeah, that's why I wanted to pass that t. Because if, for example, in the example, we have an array that hits like this. We are going to traverse this right ABB first. We're going to do triangle intersections, and we're going to hit this triangle. Then what we do is to basically say, okay, the length of this array now is until here. And if we go traverse, if we're further on in traversal somewhere, we might not hit a box like this anymore. Like, for example, this one might also have children, like these. Like, we're going to traverse this box since we put it on the stack. Oh, I have something selected, I think. Yeah. We're not going to hit either of these boxes, because the length of our array will be until this. So if hit left and t left is less than t, or it's greater than t, we'll say hit left is false, and do the same for hit right. I think that's all. Let's see if this works. So I'll say bool hit equals the intersection of this, which takes the array, and some t value. So we'll just output the t, and that does not equal -1. Let's see if any of the stuff I've been writing so far will work. Oh, this should be root nodes, min and root node max. We should be seeing a nice little bunny if I could not make as many mistakes. We need a dummy t. Child and try index. Child index and try index. Many copy-paste bugs in here. Again, oh no. That should be all. Still not. Position. Position is invalid subscript for vertex. Did I make a typo? Yeah, I made a typo. Struct rate of flow 3. Right, yes. Because we changed this. And I mistyped. Oh, this should be reflection ray. Oh, we need to output t right here, t right without having been initialized because I passed the wrong parameter here. Oh, I'm expecting lots of bugs in here. Just based on the number of compilation errors. Let's see how slow it gets. It's not hitting anything. It's also not becoming slow, which also concerns me. And we also don't see our triangles anymore. Well, we weren't gonna see them anyway because we don't do anything with refraction anymore. Um, let's actually get rid of that whole refraction thing then. Will this actually look nicely in our IDE? Can I collapse this? Yeah, this will save us a bit of. Oh, like we won't have to look at as much code anymore. Cool. These comments also don't make any sense anymore. Undeclared identifier T. That probably doesn't fix anything, but it cleans up the code a bit. So let's see if this even. Can we? I did that wrong. Now it's just if it misses, I'm gonna output 1. Oh yeah, we can. So I've got the inverse of what I wanted. Like we'll return. We'll just say we hit a triangle. If we hit the first ABB. So this works. Then we make the current node index the root node. We're gonna load that node. There's duplicate load in here, but I'm not gonna worry about that for now. We'll check if the triangle count is 0, which will be 0. Then we'll load the child left, child right. What happens if I get rid of this? Will this solve our problem? Because this is just optimization. No, still broken. We can also say it hits left or hits right or 0 as test. See if we hit any of the child nodes. Yeah, we do hit the child nodes. And you can see in the size of the boxes that it seems to be doing that right. Then if we hit T and if we hit left and right, we'll put these here based on the order. If we didn't hit both and we hit left, we'll traverse left. If we didn't hit both and we hit right, we'll traverse right. Otherwise, put little thing from the stack. Perhaps this code is just completely wrong. Let's say if we hit leaf node, we'll return 0. So we never hit our leaf nodes. Or we do on this one spot. Is that correct? Like we should always be hitting leaf nodes. I'm also not sure how high our stack index is getting. Perhaps we're overflowing our stack without me noticing. so much to think about. So let's not sort. Let's just always go in this one direction. And let's get rid of that skybox. Oh, why are you not collapsed? So we can see our results a bit better. Yeah, just like I was expecting, lots of bugs. Let's add some comments and read the code. Perhaps we find it as we're reading through it. So we load the left and right children. Then we intersect with left and right children. If we hit both, add right child to stack, traverse left child. Let's just go, if we hit this case, what happens then? So we skip this else, we skip this else. Yeah, this aligns with that, right? With that else. Yeah, so we just go here, go back to the start of the loop. We load that node. Which again is double loading a node. Oh yeah, that's one of the things I wanted to try that I just remembered is store child ABBs in BPH nodes. Instead of storing the ABB itself, store the ABBs of the children. Because if it's a leaf node, we don't even check for the children, and we don't have to load the children's nodes. It just makes a lot of sense for traversing. So we take child left, min and max, the origin, reciprocal T left, right min and max, origin, reciprocal traction T right. Okay, let's add like a less efficient but easier to grasp case. So if hit left, we add left to the stack. If hit right, we add right to the stack. Then we'll just simply check if the stack is empty, we quit. Otherwise, pop the item off the stack. That gives the same results. Let's just add these variables for convenience. The compiler will optimize that out anyway. Oh. So this seems correct to me. Perhaps this code is just completely bonkers. But it also seems weird that we're not hitting a lot of child nodes. And when we hit the child node, we don't hit any triangles. Let's see. Test if there's anything left to traverse. If that's not the case, we will stop traversal. Otherwise, we pop a note of the stack to traverse. Add child indices to the stack if they hit. What we can also do is, instead of breaking, we can return based on where we stopped traversal and render a different color. So we'll make this a try hit instead of -1. If try hits equals 1, we'll make you blue. Else, if try hit equals 2, make green. And otherwise we'll make you white. Let's see what that looks like. Perhaps it will tell us a bit about what is going on. So it's all blue and a little bit of green. That's actually very interesting. So that would mean that most of the time we exit here because our stack is empty. So that means we're traversing inner nodes without ever hitting a child node. That seems very unlikely of happening. I know what might be up. I know exactly what might be up. And this is like, oh, this is a nasty bug. This is a nasty, nasty, nasty bug. Remember when we were creating the shader resource views for the BVH nodes? We passed an element width. But I don't think we should be passing the element width. So if we look at this data that we need to fill, oops, This is a union, the element width, with num elements. I think it might be looking at num elements and not element width, which means we are just loading 32 elements because the size of a BVH node is 32 bytes. Yeah, I think that's the bug. Oh, that's a nasty bug. That's a nasty, nasty, nasty little bug we got there. And then this should be vertex count. But it would explain why it's going wrong, because we're suddenly traversing a bunch of nodes that have ABBs all 0. And we always fill on the inner nodes. There we go. That's more the shape I was expecting. Oh, nasty little bug that was. Nasty, nasty bug. Let's turn these back into breaks. And let's change this so we return 1 if we hit a triangle. Oh, that bug is so horrible. It also explains why we could only hit that like one tiny part. There we go. We have a ray traced reflection rabbit with a frame time that's getting way too high. It's also very unstable, probably because I'm recording. It seems to be when I'm moving that's really unstable, and if I stop? No, it's just unstable, okay. But we are reflecting that bunny, which is awesome. Awesome, awesome, just awesome. Now let's add back the little optimizations I was already doing. Where we don't just simply always push and pop to and from the stack. Let's do these extra checks. And I want to add these convenience. Ooh. Zooming out the text. Add these convenience variables that we made to make it a bit more readable. Yeah, right. If we hit left, we will traverse left. If we hit right, we will traverse right. And if we don't hit anything, we pop an item off the stack. I will also test that if our array is actually too short, we will not traverse the ABB. That's a lot better. That's also, well, that like halved the rendering time, that little trick. Awesome, awesome, absolutely awesome. Super happy with this. Let's take a look at our goals for today. So we implemented stack-based BVH traversal. So I have a few things left, but I'm not sure if I want to do those right now. Yeah, I've been streaming for 3 hours now. I think I shall end the stream here for today. So I would like to thank anyone who has been watching for watching. Also the people who are watching the archive, thank you very much for watching. And I shall see you next time. Goodbye.